Very good morning, students.
Good morning, sir.
Good morning, all of you. Last class, we were discussing about the concept of dilution. So, this was a point of discussion. If you do the dilution, that means on increasing the dilution, conductance G increases. For strong electrolytes, it increases because of decrease in the interanic force of attraction. For weak electrolyte, it increases because alpha degree of dissociation is directly proportional to volume of the solution. On dilution, specific conductance decreases because on dilution, number of ions in 1 ml of the solution decreases. And molar conductance or molar conductivity or equivalent conductance and equivalent conductivity, they will be increasing because with dilution, normality of molarity, they are going to decrease. So these are the points which we have explained clearly in the last session. Now try to answer this. Which statement is not correct? Conductance of an electrolytic solution increase with dilution. Conductance of an electrolytic solution decrease with dilution. Specific conductance decrease with dilution. Equivalent conductance increase with dilution. Which statement is not correct? Conductance of an electrolytic solution increases with dilution or decreases with dilution. Conductance G is going to be
Decreased with dilution.
that is the incorrect statement. An increase in equivalent conductance of a strong electrolyte with dilution is mainly due to. Try to answer this. An increase in equivalent conductance of a strong electrolyte, that is mainly due to what?
Increase in number of ions.
An increase in equivalent conductance of a strong electrolyte with the dilution. With the dilution in a strong electrolyte, number of electrons is always there, right? Number of electrons, number of ions are same because it is a strong electrolyte. Because if I take this much volume, like HCl, I take in this much volume, it undergoes complete dissociation. If I add more water, the H plus and Cl minus ions are same or not? Number of ions are same because HCl already completely dissociated. Increase in ionic mobility of ions, that is true. Because with the dilution, what happens? The electrostatic force of attraction between oppositely charged ions, that is decreasing. So because of that, mobility increasing. Yes or no? The highest electrical conductivity of the following aqueous solution is of acetic acid.
0.1 molar difluoroacetic acid.
Yeah, more number are there. Like first option, third option, and fourth option: fluoroacetic acid, acetic acid, and chloroacetic acid. So there was only one electron withdrawing group, and that electron withdrawing group is because of inductive effect. But in the option 2, we have 0.1 molar difluoroacetic acid. Difluoroacetic acid means CHF2COOH. That CHF2COOH dissociates to give CHF2 CF bonds and C double bond O minus plus H plus. So look at the stability of this particular. So this is already having negative charge. So this fluorine is a electron withdrawing group. So this total CF2H, that will be electron withdrawing. So it withdraws the electron and means stabilizes the conjugate base. Okay. More stable conjugate base. More stable conjugate base. More stable conjugate base means more acidic, more acidic. More acidic means more number of ions, more number of ions, more number of ions means higher conductivity. Yes or no? The conductivity is going to be higher for CHF2COH because of dissociation of the OH bond. Whatever the conjugate base we obtain, that is more stable because of electron withdrawing tendency of the CF bond. Because of that, more number of ions are there, so higher will be the conductivity. Which has maximum conductivity? Maximum conductivity is shown by species having more number of ions. Species having more ions. So in first option, no ions, 0 ions. Here we have 2 ions. Third option, 3 ions. In the fourth option, we have a complex ion and 3 counter ions, 3 chlorides. So 4 ions are there in the option 4. So option 4 will obviously show the maximum conductivity. Right? Very good. Determination of molar conductance of electrolytes at infinite dilution. This is also important. Infinite dilution. Infinite dilution means what? Infinite dilution means we are adding extra or excess amount of water. Greatly, we are adding water. I'm taking water as solvent. So molar conductance increases or decreases? If you try to
Increases.
understand the concept here, molar conductance, equivalent conductance, and conductance, they are all going to be increasing with dilution. Only specific conductance decreases. So what we say is Debye-Huckel-Onsager equation is molar conductance at any concentration is equals to molar conductance at infinite dilution minus some constant A into root C. This is nothing but your Debye-Huckel-Onsager equation. This is only applicable for strong electrolytes, where delta M at a concentration C is the molar conductance at any concentration C. Delta M at infinite is molar conductance at infinite dilution or limiting molar conductance. Why? Limiting molar conductance, delta M at infinite dilution is the maximum conductance shown by that solution, shown by that electrolytic solution. Why? Because of dilution, what is happening? The concentration is decreasing. Because of decrease in concentration, the molar conductance is increasing. So molar conductance at infinite dilution is nothing but the limiting molar conductance. A is a constant and its value is particular for a particular type of electrolyte. That means if you take some KCl type of electrolyte, KCl gives K plus and Cl minus ions. So one cation, one anion, it is 1:1 type. NaCl gives Na plus and Cl minus. It is also 1:1 type. CaCl2, BaCl2, they are 1:2 types. So for the same type of electrolyte, you will be having same value of A. So molar conductance at any concentration is equal to molar conductance at infinite dilution minus some constant A into root C. This is nothing but your Debye-Huckel-Onsager equation, which is only useful for strong electrolytes. And the value of A will be same for a particular type of electrolyte, and the value of A for a given solvent and temperature. Solvent is fixed and temperature is fixed, depends only on the type of electrolyte. That is what type the electrolyte is. For example, NaCl, KCl, they are 1:1 type. MgCl2, CaCl2, they are 1:2 type. So for MgCl2, CaCl2, we have same value of A. Now let us try to understand the plot of molar conductance at any concentration versus your root of C. So let us try to draw a graph. Let us try to draw a graph. Molar conductance at any concentration I'm taking on the y-axis, and molar and root C I'm taking on the square root of C concentration I'm taking on the x-axis. So what was our equation? Molar conductance at any concentration is equals to molar conductance at infinite dilution plus of minus A into root C. So this is y is equals to C plus m into x. So you have slope as minus A, you have y-intercept as molar conductance at infinite dilution. But can we achieve infinite dilution? Is infinite dilution achievable?
No, sir.
We are just saying practically that we are doing infinite dilution, but is that real? No, it's not real, because we cannot dilute, we cannot add extremely high amount of water. That's what infinite dilution means. So what we are going to do is how to plot a graph. So what I'll do is I'll measure the concentration I can measure. This A value is fixed for fixed type of electrolyte. So at a particular value of concentration, I'll measure the molar conductance at that particular concentration. So how to, like, if you have y is a function of x, if you go with the mathematical analysis, if y is a function of x, the value of y you will find out for every value of x. You will get a point. Yes or no? For every value of x, you will get a value of y. That means x comma y you are getting. That x comma y is a point in the graph paper which you can note. Like that, you will be getting many points. Like for every value of x, you will be getting a different value of y. Like that, you will get a set of points. You try to connect all those points, you will be getting the respective graph. And for your graph to be perfectly good, like if I measure the value, like root C is some 5 here, for example, I'm saying, and you have measured the value of delta m naught, it was somewhere here. So this is one point. And at root C, you are measuring at 10. or 15, let us say. At 15, you are measuring the molar conductance. The point was somewhere here. Now, if the 2 points are different, no, this interval is different. Now I connect the 2 points with the straight line, or I can connect with the zigzag line, or I can connect with the curved line. Any line I can choose. So to have a particular perfect graph, what should I do? To have a perfect
Small
graph,
values are taken.
yeah, I have to reduce the, or I have to measure the value of delta m at any concentration for every value or very small intervals of root C. Yes or no? That's what we are going to do. For every small intervals of root C, if I try to measure the molar content and E concentration, I'll be getting some specific points. And obviously, we have the equation as well. This equation, you may ask, sir, how do we get this equation? This equation was framed after measuring the graph. This is no, from the equation, we are not plotting the graph, students. You understand this point carefully always. No scientist will try to write the equation first and frame the graph. Never. He framed the graph first. From the graph, he tried to write the equation. Okay. We don't know the equations. How do you know? No one will come to you and say this is the equation randomly. So we have to develop that equation. So we have to understand the experimental data. So that experimental data, whenever you try to plot for molar conductance at any concentration of root 3, that was found to be in this manner. So you are getting straight points, different points in this manner. So it should be a straight line. Yes or no? Yes or no? It should be a straight line. But you cannot measure the molar conductance at concentration 0 because I can't make the concentration 0. Practically, that is not possible. Theoretically, I can say infinite dilution. So concentration was 0. But practically, is it achievable? No. So to measure the molar conductance at infinite dilution, what I can do is I can simply extrapolate this curve. Yes or no? I am getting a straight line. Like I have to reach this particular wall, and I know a straight line is passing. I can only draw the straight line up to here. I don't know the points over that. So what I'm doing is I'm just continuing with that line. Same thing, up to here I can measure because at low concentration. Below that, the concentrations, very low concentrations, I cannot make it, and I cannot measure the molar conductance. That is why what I'm doing is I'm just doing the extrapolation. Extrapolation of the straight line will be actually finding out the molar conductance at infinite dilution. So molar conductance at infinite dilution is the respective y-intercept, and slope is nothing but minus a. So slope is negative. Yes or no? This is for the strong electrolyte like HCl or KCl. For HCl or KCl or strong electrolyte. For the weak electrolyte, how to find out? Strong electrolyte. For weak electrolyte, how to find out? For weak electrolyte, let us say Ha dissociate to produce H plus and A minus. Again, we have Ostwald's dilution law. At time t is equal to 0, we have concentration C 0 0. At time t is equal to t, we have C into 1 minus alpha, C alpha and C alpha. So K is equal to C alpha into C alpha by C into 1 minus alpha. C gets cancelled out. So you will get C alpha square by 1 minus alpha, or K is equal to C alpha square, since 1 minus alpha is approximately equal to 1. So K is equal to C alpha square. What is alpha? From the experiments of conductance, alpha you can write as molar conductance at any concentration by molar conductance at infinite dilution whole square. So you can write K is equals to C into molar conductance at any concentration whole square divided by molar conductance at infinite dilution whole square. So from here I can write molar conductance at any concentration whole square into C is equals to K into molar conductance at infinite dilution whole square. So from here what I can write, molar conductance at any concentration into root C is equals to root K into molar conductance at infinite dilution. So I am getting this equation. So how does this equation look like? Molar conductance at any concentration versus root C, that is xy is equal to some C square. So it resembles a graph like xy is equal to C square. Xy is equal to C square is a rectangular hyperbola. Rectangular hyperbola. Yes or no? So rectangular hyperbola means you will be getting a curve like this. This is for weak electrolytes, and this is for strong electrolyte. For strong electrolyte, you are getting a straight line, where if you do the extrapolation of that straight line, extrapolation means I can measure the values only up to a specific concentration. Below that concentration, the molar conductance I cannot measure. So that's what I'm doing is I'm just drawing the straight line in that direction with the same slope only and meeting the y-axis. So that is nothing but extrapolation. So due to extrapolation, I can measure the molar conductance at infinite dilution for strong electrolyte. But for weak electrolyte, can I do that? For a weak electrolyte, the molar conductance at infinite dilution, can I measure by extrapolation? No, because for weak electrolytes, you are getting a rectangular hyperbola whose slope is not fixed. I can do extrapolation only when the slope is constant. No, if the slope is not constant, I don't know how to bend, how to measure. So for weak electrolyte, since the graph is rectangular hyperbola, you cannot do the extrapolation and measure the limiting molar conductivity. Is that point clear?
Yes, sir.
Yes. So you have the same scenario, molar conductance at any concentration of root C. If you try to measure, you will be getting a graph like this. For KCl strong electrolyte, you have plotted a graph only up to this point because you don't know, you can't measure the at lower concentrations or concentration 0, you can't do the extrapolation. Like you can't measure, you can just see that. Yes or no? Up to here you can measure the values of molar conductance, but at lower concentrations or concentration 0, you can't measure the conductance. So that is why you are going to have do the extrapolation and do the measure the molar conductance at infinite dilution. This is for a weak electrolyte CHCOH. The graph will be looking like rectangular hyperbola. Yes or no? And you have some specific points. Kohlrabi is not this one. If a graph is plotted between molar conductance and root C, a straight line is obtained for strong electrolyte. For strong electrolyte, what is obtained? A straight line is obtained. On extrapolation, this line touches y-axis, that is molar conductance at any concentration axis. Therefore, for strong electrolyte, molar conductance at infinite dilution can be found from the intercept. For weak electrolyte, the slope of the curve is not constant. It is rectangular hyperbola, right? It is moving in the direction, so it cannot be extrapolated to obtain the molar conductance at infinite dilution because you have this curve. Like molar conductance at any concentration into root C is equals to root K into molar conductance at infinite dilution. It resembles rectangular hyperbola. Rectangular hyperbola. Right. So then comes your Kohlrabi's law. Kohlrabi's law states that at infinite dilution, when dissociation of electrolyte is complete, understand this point carefully. At infinite dilution only dissociation will be complete. Yes or no? Because K, even though you take a weak electrolyte, for acetic acid also we write the molar conductance or equivalent conductance of acetic acid is equals to the equivalent conductance of acetate ion plus equivalent conductance of H plus ion. You write like that or not? But we all know acetic acid is a weak electrolyte, weak acid. But what we are saying, at infinite dilution, when the dissociation of electrolyte is complete, that means at infinite dilution, so K is equal to C alpha square. K is equal to C is number of moles by volume into alpha square. So alpha is directly proportional to under root of V. So if you are doing the dilution, at infinite dilution, what happens? Volume is going to be very high. If volume is very high, alpha will be very high. If alpha is very high, you can assume the weak electrolyte also to be a strong electrolyte where the dissociation has been done completely. At infinite dilution, when dissociation of electrolyte is complete, each ion makes a definite contribution. You don't need to think like, sir, there are undissociated ions also. Like undissociated molecules are also there, right? No, because infinite dilution means all the molecules have been dissociated. At infinite dilution, when dissociation of electrolyte is completed, each ion makes a definite contribution towards equivalent conductivity of any electrolyte, irrespective of the nature of ion associated with it. So even though you take acetic acid, even though it is a weak electrolyte, but at infinite dilution, the equivalent conductivity of acetic acid is the sum of equivalent conductivities of both the cation as well as anion. So that will be your formula. This law states that equivalent conductivities of any electrolyte at infinite dilution is the sum of ionic conductivities of the cation and anion given by the electrolytes at infinite dilution. And for a particular molecule or for a particular electrolyte, I can use this symbol, delta or lambda, both I can use. But for the ion, you have to use lambda only. For ions, only lambda has to be used. Mostly only lambda is used for ions. But for electrolytes, you can use delta, that is lambda, or this reverse V symbol delta. Right? So where lambda C infinite is the equivalent conductance of cation at infinite dilution. Lambda A infinite is the equivalent conductance of anion at infinite dilution, like we have acetic acid CH3COH dissociates to produce CH3CO minus and H plus. So dissociation is complete at an infinite dilution. So we have molar conductivity or equivalent conductivities of acetic acid at a infinite dilution is equals to equivalent conductance of acetate ion. For ions, you have to use lambda. So lambda equivalent of CH3CO minus for at infinite dilution plus lambda equivalent of H plus at infinite dilution. So equivalent conductance of cation at infinite dilution and equivalent conductance of anion at infinite dilution, whenever you try to add them, then only you can say uh, that is nothing but your equivalent conductance of the electrolyte. You should say that 100% dissociation occurred because of infinite dilution. AXBY dissociate to produce XAY plus YBX minus. So if you try to write in terms of molar conductance at infinite dilution for AXBY is equals to, we have XAY plus, so X into molar conductance of cation at infinite dilution plus Y into molar conductance of anion at infinite dilution. So that will be your respective formula. X into molar conductance of cation at infinite dilution and Y into molar conductance of anion at the same infinite dilution. And X and Y are stoichiometric coefficients of cation and anion. All have the same meaning. All of them have the same meaning. Is that clear, students?
Yes, sir.
Yes, right. The maximum ionic conductance of K plus Al plus 3 SO4 2 minus or X, Y, and Z. Calculate limiting molar conductance, limiting molar and equivalent conductance of potash alum. So try to calculate molar conductance at infinite dilution of K2SO4 dot Al2SO4 taken thrice dot 24H2O is equals to, it is giving 2K plus ion. So 2 into, it gives what? 2K plus 2Al plus 3 plus 4 sulfate, 4SO4 2 minus. So 2 times that of molar conductance of K plus at infinite plus 2 times that of molar conductance of Al plus 3 at infinite plus 4 times that of molar conductance of sulfate at infinite. That is equal to, what is K plus ion? K plus is X, 2X plus Al plus 3 is Y, 2Y plus 4Z. Okay, this is nothing but your molar conductance in Simon centimeter square mole inverse. They are asking equivalent characters. Similarly, equivalent conductance at infinite dilution for alum is equals to molar conductance at infinite dilution divided by n factor. What is the n factor? Molar conductance is 2x plus 2y plus 4z. What is the n factor for potash alum? 8. 8 is Simon centimeter square gram equivalent inverse because it is equivalent conductance. Since it is equivalent conductance, you should write the gram equivalent inverse, right? Such type of simple questions can be asked. Let us look at the applications of Kohlrausch's law as well. So to calculate the limiting molar conductivity of an electrolyte, limiting molar conductivity of an electrolyte can be calculated when you know the limiting molar conductivity of different electrolytes. How to do it? Like if molar conductance of NH4Cl is x1, ohm inverse centimeter square mole inverse, KOH is x2, KCl is x3. We have to find out for NH4OH. How to find out for NH4OH? So can I write these equations? Molar conductance of NH4Cl at infinite dilution is equals to molar conductance of NH4 plus at infinite plus molar conductance of Cl minus at infinite. So molar conductance of NH4 plus at infinite. Let us write the equation for all. NH4Cl, KOH, for KOH you write down molar conductance of KOH. Since I have told you for electrolyte you can use lambda or delta, both you can use. Molar conductance of K plus at infinite plus molar conductance of OH minus at infinite. Similarly, molar conductance of KCl at infinite is equals to molar conductance of K plus molar conductance of Cl minus at infinite. Now we have to find out molar conductance of NH4OH, right? So molar conductance of NH4OH is equals to molar conductance of NH4 plus at infinite plus molar conductance of OH minus at infinite. Yes, molar conductance of NH4 plus. NH4 plus, how to write down? Where is NH4 plus available? First equation. So can I write? Yes, molar conductance of NH4Cl at infinite minus molar conductance of Cl minus at infinite. Because I'm taking this Cl minus molar conductance of Cl minus at infinite relation to the other side. So from here I can return the value of molar conductance for NH4 plus. Similarly, molar conductance of OH minus, how we can write? OH minus where it is available? Second, molar conductance of KOH at infinite minus molar conductance of K plus at same infinite. So I can write the same expression as molar conductance of NH4Cl at infinite plus molar conductance of KOH at infinite minus of molar conductance of Cl minus at infinite plus molar conductance of K plus at infinite. Molar conductance of K plus and Cl minus is nothing but KCl or not. That is equals to molar conductance of NH4Cl at infinite plus molar conductance of KOH at infinite minus molar conductance of KCl at infinite. So with the help of three electrolytes, I can actually measure the molar conductance of an unknown electrolyte or not. To calculate limiting polar conductance of an electrolyte, this Kohlroth's law is useful. Is that clear?
Yes.
That is nothing but NH4Cl is X1
X1 plus X2 minus X3.
minus X3. Unit is same. Ohm inverse, centimeter square, mole inverse. Right. The same question, right? NH4Cl, KOH, KCl. This is nothing but X1 plus X2 minus X3. Ohm inverse, centimeter square, mole inverse. Next one is to calculate the degree of dissociation. To calculate degree of dissociation, what was the formula you can use? Alpha is equals to molar conductance at infinite dilution. Molar conductance at any concentration by molar conductance at infinite dilution. That is also equal to equivalent conductance at any concentration by equivalent conductance at infinite dilution. So these are the formulae used to calculate the degree of dissociation alpha from your respective molar conductance at any concentration and molar conductance at infinite dilution. You may ask a question, sir, how it is related to Kohlroth's law? I'm writing this in the application of Kohlroth's law, but how it is related? We can say that this molar conductance at infinite dilution that was actually interpreted using Kohlroth's law. Yes or no? This was calculated using Kohlroth's law. So that is how it is also an application of Kohlroth's law. Degree of dissociation alpha is equal to equivalent conductance at a given concentration divided by equivalent conductance at infinite dilution, or molar conductance at given concentration by molar conductance at infinite dilution. These are the respective formula. Alpha is equals to molar conductance at any concentration by molar conductance at infinite dilution. From there you can write K is equal to C alpha into C alpha by C into 1 minus alpha. So you can write K is equal to C alpha square by 1 minus alpha. You can also write, if alpha is less than 5% or 0.05, then 1 minus alpha you can approximate to 1. So K is equal to C alpha square. From K is equal to C alpha square, you got the equation K is equal to C into molar conductance at any concentration by molar conductance at infinite dilution whole square. Square root, take the square root on both sides. Root K is equals to root C into molar conductance at any concentration by molar conductance at infinite dilution. Therefore, molar conductance at any concentration into root C is equals to root K into molar conductance at infinite dilution. This is nothing but rectangle hyperbola. This graph also we have plotted. If you remember, we have plotted the graph or not?
Yes, sir.
Yes or no? This is nothing but rectangular hyperbola. Xy is equal to C square. Then the next application is to calculate the solubility. This is also important. What does this application means? To calculate solubility S and KSP of any sparingly soluble salt. Sparingly soluble salt means what, students? Sparingly soluble salt means the salt is slightly soluble or less soluble. Yes or no? The solubility is less. Sparingly soluble salt means they are less soluble. saturated solution of a sparingly soluble salt. Understand this point? Sparingly, like NaCl, AgCl is a sparingly soluble salt. Let us say AgCl I am adding to this water. AgCl, if I add to water and I just still some amount, like just a pinch of AgCl added, it has been dissolved. Some more added, even more a slight amount, that is also dissolved. Even more slightly added, that is also dissolved. Like that, I can generate a saturated solution where no more AgCl will dissolve, because it is sparingly soluble. It will dissolve only to a very less extent in a particular solvent. So whatever the saturated solution I generate, for that saturated solution, you can imagine or you can approximate the saturated solution of a sparingly soluble salt as infinitely diluted solution. Understand this point carefully. For a sparingly soluble salt, saturated solution of sparingly soluble salts, you can approximate to it is an infinitely dilute solution. That means, even though you say 1 mole of AgCl is added in this much ml of water, even though you are able to calculate the concentration of AgCl, you have to assume it as a infinitely diluted solution. Everyone got this or not? For a sparingly soluble salt, the saturated solution of a sparingly soluble salt is approximated to be infinitely diluted solution. Infinitely diluted solution. So whenever you approximate that, that means molar conductance at that particular concentration is also approximated to molar conductance at infinite dilution. And whatever the concentration we have at that time, that is nothing but the molarity you will replace with solubility S. Okay. So whenever molarity you are replacing with solubility, you have to replace molar conductance at any concentration to molar conductance at infinite dilution. These are the approximations. Yes, look at the equations. Sparingly soluble salt means salt with very less solubility. Saturated solution of sparingly soluble salt can be considered as infinitely dilute solution. Infinitely dilute solution. In a saturated solution of sparingly soluble salts, in a saturated solution of sparingly soluble salts, what you can say is, if a molarity is equal to solubility, then molar conductance saturated is equals to molar conductance at infinite dilution. Even though you can measure the concentration, yes, that is true. You can say its solubility is 0.01, like this much is solubility, this much is the concentration, like that you can say. But since it is a saturated solution of sparingly soluble salt, whose solubility will be less, you have to approximate that to be infinitely diluted. Why? You may ask the question, sir, why? Why you are saying to approximate me that why the saturated solution has to be infinitely diluted? Because the salt itself is sparingly soluble, it has a very less solubility. Whatever the salt you are taking, that salt is completely soluble in the saturated condition. Yes or no? Saturated means what? Whatever the salt you have taken, that is dissolved completely in that particular solvent. Since its solubility is less, it is completely dissolved means the whatever solvent we have taken, that should be maximum. So it can be approximated like that. Got it now? It's not like approximation. Since it is saturated, whatever the solute it has to dissolve, that has to be dissolved in a particular solvent which has to be maximum amount, because it is a sparingly soluble salt. Its solubility is less. So molar conductance saturated is equals to, so we know this formula, molar conductance at any concentration is equals to K into 1000 by molarity. Here K is in ohm inverse, centimeter inverse. Molar conductance at any concentration for a saturated solution. Molar conductance at any for saturated solution of sparingly soluble salts is equals to K into 1000 by molarity, but you can approximate this as molar conductance at infinite dilution, that is equals to K into 1000 by solubility. From here I can write the solubility S is equals to K into 1000 divided by molar conductance at infinite dilution. From here I can actually measure the KSP. From here we can measure KSP, solubility product. We can also measure based on the type of salt given to you. Is that clear, students?
Yes.
So let us try to solve some examples, then you will be getting clarity. So molar conductance at infinite dilution for H2CO3 is how much? How to measure this? So I can simply write molar conductance at infinite dilution for H2CO3 is equals to H2CO3 gives 2 H plus ions, so 2 into molar conductance of H plus at infinite dilution plus 1 carbonate ion plus molar conductance of CO3 2 minus at infinite dilution. Now look at the H plus ion. Where is H plus available? And first look at the units. They were asking us to calculate molar conductance, but in the given information, the units are first K2CO3 Simon centimeter square mole inverse. For H2S4 Simon centimeter square equivalent inverse. So what is the conductance given to you? Molar or equivalent?
Equivalent.
Equivalent. Molar conductance at infinite dilution of K2CO3 is 285. Molar conductance at infinite dilution for H2S4 is how much? 2 into 430. Because it is equivalent conductance given to you. Molar conductance at infinite dilution for K2SO4. What is the N factor for K2SO4? Again 2.
2.
2 into 153.5. Now we have to find out H plus ions. From where you will get the H plus ions? H2S4. H2S4 gives 2 H plus ions and 1 sulfate ion. So I can write this expression as molar conductance, the same thing. Molar 2 H plus ions I will write as molar conductance at infinite dilution of H2SO4 minus molar conductance at infinite dilution of sulfate. Can I write like this or not? Because H2S4 gives 2 H plus ion plus 1 sulfate ion. That sulfate ion I am removing out. So I am writing the just a contribution towards molar conductance of Chris asks, sir, can we directly write it as molar conductance of K2CO3 plus molar conductance of H2S4 minus molar conductance of K2S4? No. Why? Because they have not given the, like we have H2 as H2CO3. Yes or no? So in case that may be true whenever the n factors are all same. Whenever the n factors are differing, somewhere you will be getting half also. Okay, you don't directly write in that manner. So whenever the n factors are same, that will be true. Now also we can reduce the same equation, but whenever the n factors are different, here K2CO3, H2S4, K2S4, the n factors are same for all the 3 cases. That is why that equation might be true. That is just a coincidence, but it is not generalized. Okay. We cannot generalize that because somewhere you will be getting half as well. So we'll look at the other examples where you will get more clarity. So I can write 2 lambda of H plus infinite is equal to molar conductance of H2S4 at infinite dilution minus molar conductance of sulfate at infinite dilution. Where is carbonate's influence? K2CO3. So I can write that as molar conductance of K2CO3 at infinite minus 2 times that of molar conductance of K plus at infinite. So I can write as molar conductance of H2SO4 at infinite plus molar conductance of K2CO3 at infinite minus of 2 times that of molar conductance of K plus molar conductance of SO4 2 minus at infinite. What is this? Nothing but molar conductance of H2S4 is 2 into 430. Molar conductance of K2CO3 is 285. 0.6 minus K2SO4 is 153. The unit is Simon centimeter square mole inverse. Even though they ask equivalent conductance, you try to figure out the molar conductance only. Then finally convert the molar conductance into equivalent conductance because molar conductance will be very easy to calculate. Okay.
Yes, sir.
Yes, right. Try to solve this. Molar conductance of 0.1 molar acetic acid solution is 3.2 ohm inverse centimeter square mole inverse, and maximum molar conductance is 320 ohm inverse centimeter square mole inverse. Calculate pH of 0.1 molar CH3COH solution. CH3COH dissociates to produce CH3CO minus plus H plus. They are asking us to calculate pH. At time t is equal to 0, C is the concentration of acetic acid. 0 and 0 are the concentration of acetate and H plus ion. Time t is equal to t, C into 1 minus alpha, C alpha and C alpha. So what is pH? pH is negative logarithm of concentration of H plus. So that will be negative logarithm of what is the concentration of H plus? C into alpha. Do they give the concentration of acetic acid? Yes, 0.1 molar. Alpha you have to find out. What is alpha? Alpha is nothing but molar conductance at any concentration by molar content at infinite dilution. So molar content at any concentration, how much? Molar contents of 0.1 molar acetic acid solution is 3.2 ohm inverse centimeter square mole inverse, and maximum molar contents is 320. Maximum molar contents is limiting molar conductivity. So units everything gets cancels out. 3.2 by 320 is alpha is 1 by 100. So that is negative logarithm of concentration C into alpha. What is C? C is 0.1, 10 power minus 1. Alpha is 10 power minus 2. So pH is how much?
3.
3 will be respect to pH. Everyone got this or not? Yes, right. Limiting molar contents of NH4Cl is given, and ionic contents of OH minus Cl minus are given. Then calculate the molar contents of NH4OH. Molar contents of NH4OH at infinite dilution is equals to molar contents of NH4 plus at infinite plus molar contents of OH minus at infinite. So OH minus ion concentration given, Cl minus is given. So I can write this molar contents of NH4 plus at infinite plus molar contents of Cl minus at infinite plus molar contents of OH minus at infinite minus molar contents of Cl minus at infinite. Can I write like this or not? I have just added and subtracted the molar contents of fluoride ion. I can add and subtract anything. So this is nothing but molar contents of NH4Cl at infinite plus molar contents of OH minus at infinite minus molar contents of Cl minus at infinite. Now do the substitution. NH4Cl is 150, OH minus is 198, Cl minus is 76. 150 plus 198 minus 78, that will be
272.
your right answer. 272.
272.
Okay. Others check out I have just written based on your answers. Next, the dissociation constant of N-butyric acid is given, and the molar conductivity at infinite dilution is also given. The specific conductance of 0.01 molar acid solution is. What they said, dissociation constant they have given. So let us write N-butyric acid. N-butyric acid means what? CH3, CH2, CH2, COH. I can write the dissociation of that particular acid. CH3, CH2, CH2, C double bond OH. It will dissociate to produce CH3, CH2, CH2, C double bond O minus plus H plus. Some acid is given. It is obviously carboxylic acid is a weak acid. So at time t is equal to 0. We can have C00 C into 1 minus alpha, C alpha, C alpha. So K is equal to C alpha square you'll get. You will be getting K is equal to C alpha square, where K is the dissociation constant. Dissociation constant is given K, and the molar conductivity at infinite dilution is also given. The specific conductance of the 0.01 molar acid solution they are asking. Specific conductance means small k, that is also defined by K, that they are asking. So can I write the K is equal to C alpha square, that is K is the dissociation constant. Dissociation constant K is equal to C into alpha square. Instead of alpha square, I can write molar conductance at any concentration by molar conductance at infinite dilution whole square. So what is the value of dissociation constant given? 1.6 into 10 power minus 5. What is the concentration given? 0.01 molar, that is 10 power minus 2. Molar contents at any concentration we don't know. Molar contents in infinite dilution is given as 380 into 10 power minus 4 whole power 2. I can write this as 1.6 into 10 power minus 5. I can write 16 into 10 power minus 6. 16 into 10 power minus 6 by 10 power minus 2 is 16 into 10 power minus 4. 16 into 10 power minus 4 whole power 1 by 2 is equals to molar contents at any concentration by 380 into 10 power minus 4. From here I can calculate molar contents at any concentration as 4 into 10 power minus 2 into 380 into 10 power minus 4. So we all know molar contents at any concentration is equals to, what is the formula? If you look at the unit, they are asking specific contents in Simon meter inverse. So you have to write molar contents at any concentration is equals to K by 1000 into molarity. What is molar conductance in any concentration? 4 into 380 into 10 power minus 6, that is equal to specific conductance in Simon meter inverse divided by 10 power 3, 1000 into molarity is how much? 0.01. So therefore K is equals to 4 into 380 into 10 power minus 6 into 10 power 3 into 10 power minus 2. Do the calculation.
152 into 10 power minus 4.
152 into 10 power minus 4 Simon meter inverse. This is the value of K. So which is the right option then? Option 2, right? 1. Yeah, 1.52 into 10 power minus 2. 1.52 into 10 power minus 2, that will be the right option. Calculate this. These are all interesting questions. That's why I'm solving every question, so that you will be getting clarity. Okay. Like ionic equilibrium and electrochemistry, they can be interlinked in many ways. Equilibrium, electrochemistry. Next question: the conductivity of saturated solution of Ag3PO4 is 9 into 10 power minus 6 Simon meter inverse, and its equivalent conductivity is 1.5 into 10 power minus 4. KSP they were finding. For so whenever I replace molarity, if you approximate to solubility, what do you have to approximate? Molar conductance at any concentration as molar conductance.
Infinite dilution.
That is a condition, because for a saturated solution of sparingly soluble salt, molar conductance at any concentration is equals to molar conductance at the infinite dilution, because that saturated solution is obtained only when the solvent is taken in extra quantity excess, right? So now they have given the conductivity of saturated solution of Ag3PO4 K is given, and its equivalent conductivity is also given. What is the formula? Equivalent conductivity is equals to unit is Simon meter inverse. So K by 1000 into normality. This is how you can write. First, I'll convert the equivalent conductance into molar conductance. I can do the conversion or not, because I'll get the molarity directly, because we have to write in terms of solubility, right? So equivalent conductance is given like this. So molar conductance, how I can write? Equivalent conductance is equals to,
Molar conductance by n
or
plus
you can
that.
write just a second. I'll write this. Molar conductance is equals to K divided by 1000 into molarity. So he instead of molar conductance, I'll write equivalent conductance at any concentration into n factor. That is equals to K divided by 1000 into molarity. So equivalent conductance at any concentration, that you can approximate to respective molar equivalent conductance at infinite dilution. So from here I can write the solubility. S is equals to, or you can write the equation again. Equivalent conductivity at infinite dilution into n factor is equals to K divided by 1000 into solubility. So what is the equivalent conductivity at infinite dilution? Solubility is equals to K. What is K value? The conductivity of saturated solution is given as 9 into 10 power minus 6 divided by 1000 into equivalent conductance in infinite dilution is 1.5 into 10 power minus 4 into n factor Ag3PO4. N factor is how much?
3.
3. 3 Ag plus or PO4 3 minus. So magnitude of all the positive charge and negative charge is 3. So 9 into 10 power minus 6 by 1000 into 1.5 into 10 power minus 4 into 3. What is the solubility you are getting?
2 into 10 to the power minus 5.
2 into 10 to the power minus 5. Others also check it out. Okay. And now they are asking us to calculate the KSP Ag3PO4. Ag3PO4 dissociates sparingly soluble salts to give 3 Ag plus and PO4 3 minus. Time t is equal to 0. We can say concentration 0 0. Time t is equal to t. Ag3PO4 salt. We can assume 3s and s here. So KSP is equal to concentration of Ag plus whole power 3 into concentration of PO4 3 minus. So KSP is equals to concentration of Ag plus is 3s.
27 is power 4.
Yeah, 3s whole power 3 into s. So KSP is equals to 27 s power 4. So therefore Ksp is equals to 27 into S. What is S? 2 into 10 power minus 5 whole power 4. 2 power 4 is how much? 16. 27 into 16 into 10 power minus 20. 27 into 16 how much? 16 into 30.
8.6.
16 into 30. 16 3 is 480. 480 minus 48. 4.432 will get. Check it out.
Yes, 432.
Yeah, 4.32 into 10 power minus 18. So option 1. Is that clear, students? Okay, 16 into 27, right? You can write 16 into 30 minus 3. 16 into 3 is 48. 480. 480 minus 16 into 3 is 48. 480 minus 48 is how much? 432. But 432 into 10 power minus 20 is 4.32 into 10 power minus 18. So that is how you can get the right answer. For HCl solution at 25 degrees Celsius, equivalent conductance at infinite dilution is given. 425 ohm inverse centimeter square equivalent inverse. Specific conductance of a solution of HCl is also given. Degree of dissociation 90% and normality of solution is how much? Normality you are asking. Okay, HCl solution, what are given to you? For HCl solution, equivalent conductance at infinite dilution is given. So equivalent conductance they are talking about. So I'll calculate equivalent conductance at any concentration is equals to K. Equivalent conductance at any concentration is equals to K into 1000 divided by normality. Because they are giving in ohm inverse centimeter square, I will write K into 1000 by normality. How to calculate equivalent conductance at any concentration? Alpha is equals to equivalent conductance at any concentration by equivalent conductance at infinite dilution. The specific conductance of K is given. Normality how to find out. So equivalent conductance at any concentration require. Equivalent conductance at any concentration is equals to alpha. 90% means 0.9 into infinite dilution. What is the value?
425.
So that means 0.9 into 425 is equals to K 3.825 into 10 power 3 divided by normality. Therefore, normality is equals to 3.825 into 10 power 3 divided by 425 into 0.9. Do the calculation, you'll get the answer.
10 normals.
10 normal, right? The equivalent conductance of 1/32 molar solution of weak monobasic acid HA dissociates to give H plus and A minus. We know K is equal to C alpha square, right? Equivalent conductance given and at infinite dilution also given. So we can calculate alpha. Alpha is equals to equivalent conductance at any concentration by equivalent conductance at infinite dilution. At any concentration is 8. Infinite dilution is 400.
400.
8 by 400 is alpha. So K is equal to C alpha square. So K is equal to C. Concentration is given as 1/32 into alpha square. 8 by 400 into 8 by 400. 8 one time, 8 4 times, 4 1 times, 4 2 times. So 2 by 4 4 16 into 10 power 4. So 1 by 8. 1 by 8 is 1.25. Like 0.125. 1 by 8 is how much? 0.125 into 10 power minus 4 or 1.25 into 10 power minus 5. Okay. So you can do the calculation. So try to practice more. You will have to increase your speed of calculation. Okay. Whenever you practice more, then only your concentration, whenever only your speed increases. Following limiting molar connectivities are given: H2S4, K2S4, acetic acid, potassium acetate. See, earlier Chris asked a question. Sir, can I simply write molar conductance of H2S4, K2S4 and subtract some the molar connectivity? But now if you look at CHCOOK, it has a different n factor when compared to H2S4 and K2S4. Now you cannot do that. Now you are not supposed to do in that way. Rather, you will be getting different answer. Okay. So let us try to understand now how to solve. Acetic acid they were asked. Acetic acid molar connectivity at infinite dilution of CH3COOH is equals to molar connectivity of acetate ion at infinite plus molar conductivity of H plus at infinite. Acetate ion, where you get acetate ion? Look at the units. Everywhere Simon centimeter square mole units, so all are molar conductivity. Acetate ion you are getting in potassium acetate. So from there I can write molar conductivity of CH3COOK at infinite minus molar conductivity of K plus at infinite. And where are you getting H plus ions?
H2SO4.
So H2S4 gives 2H plus. So I'll write half of molar conductivity of H2S4 at infinite minus molar conductivity of sulfate at infinite. Okay, because 2H plus is actually giving the 2H plus is obtained from the dissociation of H2S4. So molar conductivity of just H plus ion will be, so the molar conductivity of H2S4 minus sulfate whole divided by 2. So now you try to add them. You will be getting molar conductance of potassium acetate at infinite plus 1 by 2 times that of molar conductance of H2SO4 at infinite minus of molar conductance of K plus half of molar conductance of sulfate at infinite. What is this, students? This is nothing but half of K2SO4 or not? Molar conductance of potassium acetate at infinite plus half of molar conductance of H2SO4 at infinite minus half of molar conductance of K2SO4 at infinite. That is nothing but potassium acetate how much? Z plus half of H2SO4 is X minus K2SO4 is Y. Got it now, everyone?
Yes.
Yes, right. So that's how we have to do the problem. Like you have to go with the original procedure. Whenever n factors are differed, then the formula is going to be changed. Equal volumes of 0.015 molar acetic acid and 0.015 molar NaOH are mixed together. What would be the molar conductivity of mixture if conductivity of CH3CONA is given? Conductivity is given, molar conductivity they are asking. Molar conductivity is equals to conductivity K divided by 1000 into molarity. So molar conductivity they are asking for CH3CONA. So what is the conductivity K for? What is the molar conductivity if the conductivity of CH3CONA is given in Simon centimeter inverse? So I have to just calculate the concentration of CH3CONA. So we know the formula.
Sir,
Yes, please.
sir, sir, here centimeters means K into 1000 by means.
Yeah, K into 1000 by, right? Yes. K into 1000 by molarity. Yes, very good. So just to try to understand how you will be getting the respective concentration of sodium acetate, CH3CONA or CH3COH plus NaOH, CH3COH plus NaOH gives CH3CONA plus H2O plus H2O. Like how many moles equal volumes? Let us say, let us volume is V. At time t is equal to 0. How many moles of CH3COH are there? 0. Concentration is equals to number of moles by volume. So concentration is given as 0.015 molar. Number of moles is equal to 0.015 into volume. So 0.015 into V. How many NaOH? 0.015 into V. 0 and 0 are the number of sodium acetate and water. At time t is equal to t, 1 mole of acetic acid react with 1 mole of NaOH to form 1 mole of sodium acetate. So can I say 0.015 into V moles of acetic acid react with 0.015 V into NaOH to form how many moles? 0.015 into V moles of CH3CONA and 0.015 into V moles of H2O. Therefore, concentration of CH3CONA is equals to number of moles of CH3CONA divided by volume of CH3COO, volume of solution in which CH3CONA is present. What is the volume of solution? Number of moles is 0.015 into V. Volume of solution is acetic acid is VML or V liter. NaOH is also V liter, so 2V. So VV gets cancels. So 0.015 divided by 2 is the concentration of CHCONA. So what is K? Conductivity 6.3 into 10 power minus 4 into 10 power 3 divided by concentration is 0.015 divided by 2. Solve it, you will get the answer. How much is the answer? 8.4 Faizan is saying. Others also check it out once. 8.4 or 84 Faizan? Okay, 6.3 again at 63 into 10 power minus 5. 63 into 2, 126 into 10 power minus 5 into 10 power minus 3, 126 into 10 power minus 2, 126 into 10 power minus 2 whole divided by 15 into 10 power minus 3. Do the calculation, you will get 84. Right? Same type of question. So you take this as homework. So we have solved many such questions. So here units have been given, two times equivalent quantities has been given, 1 molar conductivity given. They were asking molar conductivity of oxalic acid. Convert everything into molar conductivities and do the calculation. Then the next part is electrode potential, students. Up to now we have discussed about, we have not discussed about what is electrochemistry at all. We have discussed about the conductance, the resistance, molar conductivity, Kohlroth's law. The conductance part we have seen. But electrochemistry is mainly about the study of interaction of electrical energy with chemical energy. Yes or no? So now we will start the concept of electrode potentially. So the potential developed between electrode and its ions in solution is known as electrode potential. The potential developed between electrode and its ions in a solution, that is said to be electrode potential. The potential developed between electrodes and the solution of its ions at 1 molar concentration at 1 bar pressure and 298 Kelvin, that is under standard conditions, it is said to be standard electrode potential. You may ask a question, sir, why is the potential developed? The potential developed between electrode and its solution of its ions is electrode potential. That's okay. That's the basic statement. But why the potential has been developed? That is the point. Now, you try to imagine the scenario where we have taken a beaker, like in this is a water bottle I can imagine. I have placed ZnSO4 zinc sulfate, placed zinc rod. I have placed a metal rod in a solution of its ions. In the metal rod, I can say the metal kernels are there, the positively charged metal ions and electrons are there. So metal kernels, positive charges, negative charges, positive charges, negative charges, they're all present. And there's a metallic bonding, we all know. This we are dipping in the solution means two things can happen. One thing can happen is the positive ions from the metal rod, like from the rod, the metal can come into the solution. One possibility is this is a metal rod, just enlarged view. Let us say two ions come into the solution. So two plus charges are there now. They came into the solution. And left out is, how do we have? Negative charges are more now. Yes or no? I have just to consider one part, students. I have just to consider one part of the metal rod. In the one part of the metal rod, if you try to dip the metal rod in a solution of its ions, two possibilities are there. The first possibility is the metal kernels from the metal rod, they can come into the solution. The second possibility is, okay, when a metallic rod is dipped in a solution of its ions, first possibility, metal can come into a solution. Second possibility, or metal ions from solution. Metal ions from solution will deposit on the metal rod. Okay, so that means this is the first possibility where the metal ions from the rod, they have come into the solution. The second possibility is the metal ions which are present, like positively charged ions. Already 4 positive, 4 negative are there. They are going and depositing on the surface. Okay, the positive ions from the rod, they can come into the solution, or the positive ions from the solution. You can say, whenever I place, this is a metal rod. Imagine the case, this is a metal rod. I have just dipped in the solution. From this rod, the metal ions can go. The metal from the rod can go into solution. Or the second possibility, the ions from the solution, they can go and deposit on the surface of the rod. You understood the two possibilities or not?
Yes, sir.
Yes, sir.
Now, if I ask the question, when I dip zinc rod in a ZnSO4 solution, what happens? When I dip zinc rod in ZnSO4 solution, what will happen? The zinc from the zinc rod will come into solution as Zn plus 2 ions. Okay. When zinc rod is dipped in ZnSO4, zinc rod will come into solution as Zn plus 2 ions. Zn plus 2 aqueous plus 2 electrons. But whenever you try to dip copper rod is dipped in CuSO4, then what happens? Cu plus 2 aqueous
Plus
ions, they will take up the 2 electron to form, they will deposit Cu solid. So zinc rod, whenever placed in ZnSO4 solution, what happens? It is undergoing oxidation. Copper rod, whenever placed in CuSO4, what happens? It is undergoing reduction. You may ask a question, sir, from where these 2 electrons obtained? These 2 electrons obtained from the lost electrons of zinc. You may again ask a question, sir, how can you say that zinc will undergo oxidation, copper will undergo reduction? First thing is, how are you saying that potential has been developed? I am saying that two possibilities are there. Whenever I place a metal rod in the ZnSO4 or metal rod is placed in a solution of its ions, from the metal rod, the metal can come into a solution, or the metal ions from the solution can go and deposit on the metal rod. You may again ask a question, sir, why? Why this should happen? Why can't simply metal rod be there as it is without any undergoing any disturbance? The point here is that depends upon the type of crystal lattice structures, enthalpy of atomizations. Yes or no? Whenever a metal rod is placed in a solution of its ions, whether it will undergo oxidation or reduction or no change, that will depend upon the type of metallic bonding present in the metallic rod. Because the metal rod, from the metal rod, metal is coming into solution means that metal is coming into solution as an ion. Like Zn is coming as Zn plus 2, earlier it was in the solid states. That means enthalpy of atomizations, ionization energy 1, ionization energy 2, hydration enthalpies, all these account into picture. And enthalpy of automation depends upon crystal lattice structures. Crystal lattice structure depends upon size. So everything comes back to the crystal structures, everything comes back to the sizes. Yes or no? So based on all these factors, for a particular metal, whether it will undergo greater tendency of oxidation or reduction, that has been given. So whenever zinc rod has been placed in ZnSO4, zinc has a greater tendency to undergo oxidation. So zinc rod will be coming, like zinc from the zinc rod will be coming into solution as Zn plus 2 ions. That depends upon crystal lattice structures, enthalpy of atomization, sum of ionization energies, and also the hydration enthalpies of Zn plus 2 ions. Now that point is clear. So whenever I place zinc rod is ZnSO4, the zinc is coming into solution. Now let us say we have Zn plus 2 ions, Zn plus 2 ions, and the zinc rod is placed in ZnSO4, right? ZnSO4. So we have extra negative charge or positive charge on the rod? In the rod?
Negative
In the rod
charge.
we have negative charge, no? Because some Zn plus 2 come into solution means extra negative charge is there. Since this negative charge extra is there on the rod, because of this negative charge present on the rod, again in the solution we have Zn plus 2 ions. these Zn+2 ions will try to develop electrostatic force of attraction or not with the extra negative charge. Yes or no? So zinc from the zinc rod come into a solution, but once the zinc from the zinc rod come into a solution, the extra negative charge is accumulated on the rod. So that extra negative charge accumulated on the rod will attract the positively charged Zn+2 ions, and the Zn+2 will again reach the surface, and there exists a electrical double layer. Two opposite charges separated by some very small distance, they will be forming the potential, and the potential developed is nothing but electrode potential. Electrode potential is obtained due to electrical double layer formation. Understood this point or not? The potential developed between the metallic rod or electrode and a solution of its ions is nothing but electrode potential. How is it developed? Due to electrical double layer. Okay?
Yes, sir.
There are two types of electrode potentials. What are those? Oxidation potential. So whenever zinc from the zinc rod coming into solution, oxidation happened. So whatever the potential developed there, that is said to be oxidation potential. Whenever you place copper in copper rod in CS4, reduction occurred. What is the potential developed there? That is said to be reduction potential. So oxidation potential is the electrode potential for oxidation of cell. So metal from the solid state is converting into respect to metal ions and electrons. This is nothing but oxidation potential. Higher will be the tendency to get oxidized. Higher will be the oxidation potential. Oxidation potential high means tendency to get oxidized is high. Reduction potential high means tendency to get undergo reduction is high. The electrode potential for reduction of cell greater to the electrode potential for reduction of cell greater the reduction potential, greater will be the tendency to get reduced. So reduction potential means Mn plus will take n electrons to form metal solid, and electrode potential for Mn plus to M is nothing but reduction potential. Is nothing but electrode potential. So I can say this is the zinc ZnSO4 zinc sulfate solution, and zinc rod is dipped in ZnSO4, and we have another beaker where copper rod is actually dipped in CuSO4. Zinc rod dipped in ZnSO4, copper rod dipped in CuSO4, and we have placed a bulb here. Now what happens is, whenever I place zinc rod in ZnSO4, the extra negative charge is present on zinc. So where Zn is undergoing oxidation, to form Zn+2 and 2 electrons. So what is the sign of anode? Wherever oxidation occurs, it is said to be anode. What is the sign of anode? Extra negative charge is there on zinc rod. So anode is negatively charged or positively charged? Negatively charged. This extra negative charge, this will be moving through the electrical wire. Whenever some wire has been connected between zinc rod and copper rod, the flow of electrons happens. Flow of electrons is nothing but current. So bulb glows, and these electrons, they will reach the copper rod also, and Cu+2 will now take the electrons and get deposited. So this is how the flow of electrons is happen. This will occur only for a minute time. Why? Because the circuit is incomplete. Whenever the circuit has been complete, what happens? The circuit has to be completed with the help of Salter bridge. When you complete the circuit, under that condition, you will be having the glowing of bulb happening continuously and greatly. At a cathode, what happened? Reduction occurs and electrons are gained. That means Cu+2 will be taking up by 2 electrons, forming respect to Cu. The electrons which are reaching the cathode, they were gained by Cu+2 and copper is deposited. So it is again called as positively charged. Anode is negatively charged, cathode is positively charged in a galvanic cell, and this is how the circuit is going to be happening. And whatever the electrode potential of the cell is equals to oxidation potential of anode, oxidation potential, that is electrode potential of oxidation of cell plus electrode potential of reduction of cell. Electrode potential of oxidation of cell, electrode potential of oxidation of cell plus electrode potential of reduction of cell. For oxidation of cell, what you are getting? So electrode potential E of Zn to Zn plus 2 plus reduction of cell, what is happening? E of Cu plus 2 to Cu, this is E of cell. And if the same thing you have done at standard conditions, under standard conditions, what you can write? Under standard conditions, E naught of cell, you write E naught. Standard condition means you will place the like concentration of ZnSO4 and CS4 should be 1 molar, temperature should be 298 Kelvin, pressure should be 1 bar. So E naught of cell is equals to E naught of Zn to Zn plus 2 standard oxidation potential of anode plus standard reduction potential of cathode. This is how you can write the electrode potential of the total cell. Is that clear, students?
Yes, sir.
Yes.
Factors affecting the electrode potential, first one is concentration. If you try to change the concentration of the electrolytic solution, the electrode potential will change. Nature of the metal, like if I place zinc rod in ZnSO4, it undergoes oxidation, copper rod will undergo reduction. So nature of metal, crystallite sites, enthalpy of atomizations all come into picture. Pressure, temperature conditions. Standard electrode potential. Standard electrode potential is the electrode potential measured under standard condition. There are two types of standard electrode potentials. One is the standard oxidation potential, E naught of OP, and oxidation potential means where oxidation should occur. E naught of metal M2 Mn plus is nothing but standard oxidation potential SOP, and standard reduction potential. Metal from the 0 state went into +1 state. So increase in the oxidation number is said to be oxidation. Standard reduction potential, E naught of reduction potential is M metal ion in the pleasant state went to 0 state, pleasant to 0. So reduction occurred. E naught of Mn plus to Mn is nothing but standard reduction potential. For same electrode, standard reduction potential is equals to negative of standard oxidation potential. That means if I take zinc is converting into Zn plus 2 and 2 electrons. Here we have some x volt. Zn plus 2 electron converting into zinc. It will be how much?
Minus X.
Minus x volts. For the same electrode. For the same electrode, standard reduction potential and standard oxidation potential, they are same with just a sign difference. The value of standard electrode potential E naught does not depend upon stoichiometric coefficients of balance equation. Why? Because E naught is an intensive property or extensive property?
Intensive.
Intensive property, because E naught is an intensive property with a stoichiometric coefficient, it is not going to be changing. Like Zn to Zn plus 2 electrons. Like X means 2Zn to 2Zn plus 2 electrons. Like Zn to Zn plus 2 electrons. 2Zn gives rise to 2Zn plus 2 plus 4 electrons. For that also same X. Stoichiometric coefficients, even though you change, E naught does not change, but delta G changes. And E naught, since it is intensive property, you are not supposed to add E naught. Electrode potentials are not supposed to be added. Only you are supposed to add the change in the Gibbs free energies, not the electrode potentials. As per IUPAC, standard reduction potential only you have to consider. IUPAC, we have oxidation potential and reduction potential both, but IUPAC has given a rule, you consider standard reduction potential as the standard electrode potential. Whenever nothing has been mentioned regarding the electrode potential, just they said electrode potentials are so and so, then you have to consider the electrode potential given to you as reduction potentials only. Whenever they specifically mention the oxidation potential is so and so, then as per the question you have to proceed. Nothing mentioned regarding the electrode potential means you have to treat it as reduction potential. Specifically they have mentioned oxidation potential, reduction potential, then you have to go along with that question. EMF of the cell, the difference between electrode potentials or reduction potentials of cathode and anode respectively is called EMF of the cell when no current is drawn through the cell. When no current is drawn through the cell, the difference between electrode potentials of cathode and anode, that is said to be the respect to EMF of the cell. That is EMF of cell is equal to reduction potential of cathode minus reduction potential of anode. You can also write the EMF of cell as oxidation potential of anode plus reduction potential of cathode. You can also write it as EMF of cell is equals to oxidation potential of anode minus oxidation potential of cathode. Yes or no? The EMF of cell you can write in terms of reduction potential of cathode and reduction potential of anode, that is reduction potential of cathode minus reduction potential of anode is EMF of cell. EMF of cell is equal to oxidation potential of anode plus oxidation potential of cathode, or oxidation potential of anode minus oxidation potential of cathode. That is also, this is reduction potential, right? Yes. Oxidation potential of anode plus reduction potential of cathode, or oxidation potential of anode minus oxidation potential of cathode. Under standard condition, you will use E naught of cell, that is equal to standard reduction potential of cathode minus standard reduction potential of anode under the standard condition. Is everything clear, students, so far?
Yes, sir.
Yes.
Right, very good. Reference electrode. The potential of a single electrode cannot be determined, but the potential difference between two electrodes can be accurately measured. For a single electrode, you cannot find the potential, but you can find the potential difference between two electrodes. The potential of single electrode cannot be determined, but the potential difference between two electrodes can be accurately measured using a reference electrode. That means, as I have given the example, like there are two classes. In the class A or section A, top mark is 70 mark. In the section B, top mark is 99 mark. In the section B, average mark is 80 marks. Understand the scenario? There are two sections. Section A, top mark is 70 mark. Section A, top mark itself is 70 mark. Section B, top mark is 98 mark, and average mark is 80 mark. So the topper in section A is a below average students in section B or not? Like if you talk just with respect to marks, okay, if you talk just with respect to marks, I'm not judging anyone here. So just comparing marks, if you just think of the analysis, the topper candidate in the section A who scored 70 marks is a below average candidate in section B because the average mark in section B is 80. That means when you change the section, your position has been changed or not? Like what the topper, you are a topper student, you are a below average student, you are a dull student, all this is with respect to some reference, with respect to the section. Yes or no? I may be an excellent teacher now. Here, I may not be great teacher when compared to other teachers. I may be average teacher. Like that, if you compare with respect to different positions, if you try to compare, if you try to change the reference with respect to whom you are comparing, obviously your position also changes. Same thing happens. The electrode potentials, whatever the values we have measured here, they are not absolute values. They are the measured values with respect to some reference electrode, which is nothing but standard hydrogen electrode. Standard hydrogen electrode, SHE. Like if I want to measure the electrode potential of zinc to Zn+2, we know zinc will undergo oxidation. The standard hydrogen electrode, like it will have the hydrogen gas passed through a particular beaker, and inside that beaker we will be having HCl solution. HCl gives the H plus ion. The H2 gas and H plus ions will establish the equilibrium. The concept there is H2 gas and H plus ions will establish the equilibrium. So we have two conditions. If SHE can be used as anode or cathode. At anode, what happens? At anode, oxidation should occur. So H2 will be under equilibrium with 2 H plus ions and 2 electrons are lost. At cathode, reduction occurs. 2 H plus will take up the 2 electrons to form H2 gas. So for both the conditions, whether you're using hydrogen electrode as anode or cathode under standard conditions, E naught is assumed to be 0. E naught of standard hydrogen electrode is 0. That means if I want to measure the electrode potential of zinc to Zn+2, what I will do is I connect the circuit in such a way such that one half cell I'll connect zinc rod in ZnSO4. The other what I'll do, I'll connect a device here. In the other way, I'll connect the SHE. Yes or no? The hydrogen gas is actually absorbed on the platinum electrode, platinum rod, and that hydrogen gas absorbed will be in resonance or will be in equilibrium with the H plus ions. So what I am going to say is, whatever the electrode potential of the cell, that is nothing but electrode potential under standard condition of Zn to Zn plus 2 plus electrode potential under standard condition for H plus ions to H2. How I can calculate this E naught of cell? E naught of cell I can calculate from the device. Any voltmeter which can measure the potential difference. From that I can calculate the potential difference. The potential difference can be calculated using the device, not the potential of anodic half cell or cathodic half cell. This is calculated using device. This is assumed to be how much? E naught of H plus to H2.
0.
0. So can I calculate E naught of Zn to Zn plus 2?
Yes.
So whatever the value E naught of Zn to Zn plus 2 you are measuring, that is not the absolute value, that is the value assigned with respect to standard hydrogen electrode. That point you should note. Since you are assuming E naught of H plus to H2 as 0, with respect to that only you are getting the respective E naught of Zn to Zn plus 2 values. So when you change the reference electrode, the values are going to be changed. Whatever the values you see in the electrochemical series, they are not fixed. They are with respect to the primary standard electrode, that is your standard hydrogen electrode. Okay.
Yes, sir.
We do like if I want to measure the electrode potential of Cu plus 2 to Cu conversion, then where I'll use SHE as cathode or as anode?
Anode.
As anode I'll use. Then I'll be using copper rod dipped in CuSO4 as cathode. Then I'll measure. From the reading, I'll get the electrode potential of total cell. That is nothing but oxidation potential of anode plus reduction potential of cathode. Like that, we can actually use the standard electrode, that is reference electrode, to calculate the electrode potentials of oxidation as well as reduction. An electrode is chosen as a reference with respect to which all other electrodes are valued. That is nothing but your SHE. There are other electrodes also like calomel electrode, silver chloride electrode. We'll discuss about the details in the next class. Fine. Thank you all everyone. Bye.
Thank you, sir.
Thank you.
Thank you, sir.